Hey there! Welcome to Fetch's Real-Time Analytics Summit presentation, where I'll walk you through how we built our offer forecasting tool using Pinot, upgrading an existing tool from a traditional RDBMS into Pinot, yielding around 30 times speed improvements, streamlining the workflow of our sales team. First off, I can introduce myself. My name is Brendan Siegel. I'm the Sales Intelligence Platform Lead here at Fetch. We're a small but mighty team that builds self-service analytics tools for our sales teams. So we'll start with what Fetch even is, then move into what problem we had, which we solved with Pinot. Next, we'll dive deeper into how we solved it by looking at the way we ingest our data and what that data even is. Next, we'll look at the different iterations we went through with StarTree to optimize our performance as much as possible, and what query patterns this is especially optimized for. Lastly, we'll dive into the future of Pinot at Fetch. So first off, what is Fetch? Fetch is America's rewards app, where our users get rewarded every day for common behaviors and transactions, like scanning receipts, playing games, and more. They open Fetch and see offers they might be interested in from brands who are interested in them. Next, they go out and do their normal shopping and scan their receipt. We use proprietary computer vision and ML models to understand not just the text on the receipt, but what they actually bought and reward them for it. Users earn points, and when they earn enough, they can cash them out for a gift card to any one of their favorite stores, Fetch merch, or donate to charities and other good causes. We have over 13 million daily active users, and over 11 million receipts are scanned each day. Among those receipts, we identify 30 to 40 million receipt items. Think the individual specific cookies, chips, or sodas on any given receipt. We have over 1,300 live offers for our users to redeem. Those can range from buy two of a brand soda for 1,000 points to join an at-home meal kit membership for 15,000 points. Among those offers and other ways of earning points, our users collectively earn over $150,000 worth of points each day. So, what's the problem we're trying to solve? Fetch runs offers for our users, who in turn get points that turn into gift cards. For our users, these are things as simple as go buy some soda. What they might not realize is that on the back end, we run complex forecasting models using a combination of simulation modeling and heuristic constraints, which help us predict how likely they are to go buy that soda. This helps us make sure that they get an offer that's actually tailored to them. Somebody who never buys soda isn't going to randomly go buy $50 worth of soda. These forecasting models are fed using a ton of analytics about buyer behavior from users just like them who make purchases and scan their receipts to earn points. Building the base data for these models, basically just a ton of aggregations, are expensive, both monetarily in terms of compute costs in a credit-based managed RDBMS, and in time, as those RDBMSs aren't very fast when we're talking about filtering and aggregating billions of rows and doing filtering, group bys, and distincts with cardinality in the millions. Every second spent waiting for a database to spin on computing the answers is time wasted for our sales teams, who utilize the results of this tool to fine-tune their forecasts to maximize user benefits. The faster they can iterate through concepts and ideas, the faster they can get to work getting that offer live for our users. Enter Pinot, where if we can run the exact same analytics, just way faster, we can solve that problem where forecasts take minutes to generate and waste tons of time in the process. What's worth noting is this isn't Pinot's typical use case. Pinot's traditionally used for extremely high query per second rates, sub 100 millisecond results, and millisecond level data freshness from streaming data, among other things, of course, but generally that's where it excels over other databases and finds value. Not just taking a 5-minute query and optimizing it down to 15 seconds. To that end, here's some summary stats. Our main table, which stores receipt level data, has only 21 billion rows. Some real-time use cases probably generate and load that into Pinot each hour. Our highest usage table, which is used to help our application users fine-tune the forecast they want to run using demographic filters, product filters, etc., peaks at around 20 QPS. This table is more like 60 million rows. Our main transaction table averages around 2 to 3 QPS when in use, and that's the chart you see on the right. Both are extremely bursty use cases. We don't have millions of users where if even 1% of them are using our application, we still have massive QPS. This is an internal-only tool, so we only really see traffic when our internal teams are using it. Right now, that's amongst our sales and marketing teams, totaling around 300 to 400 people. So let's get into what the data looks like and how we optimized our data ingestions and query patterns to support our unique use cases. Our main data asset is a denormalized flattened table of the receipts our users scan. Each line item on a receipt is a row in our data. So think of a receipt with cookies and milk on it. That would yield 2 rows where the user, receipt, store, etc. are all the same, but the product identifiers for the cookies and milk would be completely different. Different product identifiers, categorization, pricing information, etc. We have all this product information, user demographic data, and retailer information in such a format that we could use a star schema structure. However, we want to minimize joins to dimension tables and reduce things like lookups and scans as much as possible, basically relying on our indexing and Bloom filters as much as possible. Additionally, even if we did want to do these joins and use dimension tables, we would need immense amounts of memory to store the tables. Our user table alone is near 500 gigs, so we would need massive servers to support that, since Pinot would store that data in memory on each server. Basically a non-starter. Our basic architecture is to run our curated query, which exports the exact data we need in our RDBMS, which is kicked off each night via a DAG orchestrated in Airflow. That query does all the joins we need to flatten the table and attach our enrichment data, and then copies it into a directory in S3. Pinot then picks up the data every night and does a full table rebuild and ingestion. You'll notice that I said full table rebuild and ingestion every night. This DAG also notably wipes the table in Pinot and the file ingestion task metadata to clear the watermarks. Getting partition data out of our RDBMS, where we have vast amounts of slowly changing dimensional data, would be fairly complex and expensive. It's trivial to identify the exact records that changed and why, but organizing that data and pushing an update to all the rows in that specific file for the file ingestion task to pick up would leave massive room for error. Iceberg and Delta tables were not performant in our use cases either for unrelated reasons. Regardless, the export from our RDBMS is cheap, the storage is cheap, and Pinot isn't doing anything else at 4 a.m. for us, so no harm in doing an ingestion. Because our data isn't that massive anyways, only around 1 terabyte in Parquet, it's easier to just fully reload the tables each night. We protect ourselves from failures by using a blue and green table deployment strategy. We have two nearly identical copies of each table stored in Pinot, one blue and one green. Each night, we alternate which gets updated. Our application then determines which version or color of each table to use based on if it's the most up-to-date, in an errored state, undergoing an ingestion, or anything else that would render it inaccessible or its data incomplete. If the nightly ingestion errors for some reason, then the application can easily fall back to the last stable version of the table, and there's very minimal harm while we solve the problem with the newest ingestion. It's one thing to get the data loaded into Pinot, but in our case, that was just the tip of the iceberg. Let's walk through the iterations we went through to make this performant and some query hinting which unlocked massive performance improvements for us. Our first iteration was, frankly, a dramatic flop, and it took some digging to figure out why. Here's where we were. There was no organization coming out of our RDBMS, just a simple copy into S3 using select star from table. This writes the entire table out to the Parquet files that Pinot ingests. Turns out that Pinot isn't actually that smart when it ingests data from S3. It just grabs a Parquet file, splits it into segments based on how big the Parquet is and how big the desired segments are, builds the segments, and then moves on to the next Parquet file on the list. What this means, though, is that because our RDBMS is just shipping data as fast as it can out to S3, there's absolutely no organization amongst the segments. You can see that really plainly here in our before image, which shows which segments have data from which months. Each segment here contains data from pretty much every month with no organization or locality. It's completely random. When I go query for data from May, for example, to get that information, Pinot has to open every segment since there's data from that month in every segment. Additionally, even within that individual segment, there's no specific block of rows where the May data is. So Pinot has to parse every single row in every single segment to find the data I'm asking for. That brings me to the number of segments we had. Our RDBMS lets us configure a target size for the files it exports. Setting this too low, paired with Pinot not combining multiple Parquet files into a single larger segment, meant that not only were they not organized intelligently, but there were also a massive number of them for the query engine to parse through. We were also trying to use StarTree indexes at this time. The problem there was that our cardinality is extremely high across our dimensional columns. Think over 20 columns, each with over 10,000 distinct values. Our StarTree index simply blew up the disk, trying to store all the permutations of data. To that end, you can run into a problem where it takes longer to even traverse the tree than to just do it by hand because of all the cardinality and number of dimensions. You might as well just look up the individual records at that point, since the StarTree index value may only be representing a handful of records anyways. Lastly, our servers were using hard drives, which are much slower disks than we needed. We upgraded to instance types with SSDs to boost our performance there. These issues all compounded such that our benchmark query simply wouldn't run. It would just time out after 60 seconds. Our second iteration, as you can already see by the nice gold number there, was significantly better. We basically addressed all the issues we had before. After identifying the nuance with how Pinot was building segments from offline data, we basically forced it to be organized. Now, when Pinot ingests data, the Parquets it opens only contain data that's relevant to the rows around it. You can see that here in our after. Just by adding an order by receipt purchase date from our copy command out of the RDBMS, the database is forced to sort the data before writing to S3. This results in much more organized data in S3 and achieves data locality while working within the confines of Pinot's naive way of building segments for these offline tables. Now, when I go query for transactions in May, I'm only opening up a single segment to get that data. Obviously, with our real data, we have more than 5 segments, but the principles and obvious improvements still apply. We also upped the target file size dramatically to reduce our segment count. When we had all those massive numbers of tiny segments, a side effect of having to open them all up for each query was that we could easily run into I/O and network bottlenecks. It's simply not performant to be passing around and opening hundreds of thousands of tiny files. It's much better to pass around and open one larger file with all the data you need to answer that question. In this iteration, we set a target size of 500 megabytes. That doesn't always happen exactly. We typically see between 350 and 575, but it's good enough. We also removed the StarTree index to recover our disk space and upgraded that disk space to local NVMe SSDs. These changes combined yielded us an unimaginable performance improvement, going from not even running to running in a third of a second. Additionally, this was a V2 of the benchmark query, which didn't filter for a date window, so this was much faster on 20 times the data. Our third iteration continues to refine the unlocks we gained in the second iteration. We now sort by every dimensional column in our copy command out of the RDBMS. We sort based on business relevance. For example, how often that column is being used for filtering. Sorting by cardinality is another option, but in our case, it doesn't really help because highly relevant columns might be nested behind sorting on other columns that we don't really use as often. Think the product categories with really high cardinality being split up by sorting by a user's geographic region first. Because we don't use region as often as our product categories, we'd rather get all the rows with the same category as close together as possible to force that data locality on the segments, and then sort by region later. Additionally, now that our data was organized properly, we're able to add inverted indexes and Bloom filters on pretty much everything, making it hyper fast to find data amongst our massive levels of cardinality. This brought our 1/3 of a second benchmark query down to just around 1/10 of a second, which was a remarkable improvement from where we started. The next problem we had to solve for our use case was the performance of count distincts across dozens of levels of aggregation. This can look something like, of the people who spent over $50 on soda in the last month, how many also bought my brand of soda in the last week? This involves an incredibly high cardinality count distinct and join on our user ID column. Remember, that's over 13 million users. Notably, these types of queries require the use of the multi-stage query engine. The hint above was our biggest unlock. The way the multi-stage query engine works in these queries without the query hint is that each server is going to go find relevant records, in this case soda, and for each user, perform a group by to add up all their transactions. This is the leaf node operation. Next, the leaves send their grouped results to the intermediate server, which looks at all the results from each leaf and performs a second group by to add up the results for each user ID. There's a big problem with this though. When you have such high cardinality, that means there's probably only a few relevant records for each unique grouping value on each server, or at least that's what it was for us. That means each server is performing millions of group bys across a small number of rows for each user ID. Then once those results are sent to the intermediate stage, they have to be grouped again. Instead, we use the query hint to disable this group by at the leaf node stage. We don't need each leaf to add up 1 to 3 rows from each user for millions of users when the intermediate stage is just going to have to add up the results from the leaves anyway. It's much more performant to skip those leaf stage group bys and instead let the intermediate stage deal with a slightly higher, but still small number of raw, unaggregated rows. This saves massive amounts of time since you don't do the same group by twice. This query hint was the difference between a lot of our queries simply crashing our servers because they ran out of heap, or when they did run, taking over 60 seconds. Now they run highly performantly, and those queries that took over 60 seconds now only take a few seconds, and we don't have server crashing anymore. To boil that down into a single ratio, the smaller your ratio is between total rows and the number of distinct group bys, the more it makes sense to use that query hint. Adding it all up, where are we now? Pinot is 30 times faster than our traditional RDBMS, while only being twice as expensive. In the screenshot to the right, you can see that in some query patterns, Pinot is over 100 times faster. This speed increase allows our stakeholders to have a truly iterative workflow, testing hypotheses and planning ideas dozens of times during the workday, even live during a meeting, as opposed to letting it run during their coffee break and hoping it would be done by the time they got back 15 minutes later. Pinot has been a game changer for their teams and their workflows. Soon, Pinot will be fully integrated into our fully managed B2B platform, allowing tighter integration between the forecasts our tool builds and the offers they sell, as well as open it up to even more users. This would not even be feasible without Pinot. Thanks for coming and listening along. A huge shout out to our team at StarTree for partnering side by side with us, working through our complex and nuanced problems. We couldn't have done it without you all. Thanks.